Let's continue with our discussion now about Mendelian genetics and how it applies to meiosis through chromosomal inheritance. So last time we talked about simple Mendelian systems that only have one gene with 2 or 3 alleles on it and the type of dominance that could have. But Mendel's true work was his discovery that you can look at living systems that have many types of genes controlling different phenotypes, different traits. So for example, he might look at a plant and he might look at 2 traits, height, which could be tall or short, and he might also look at flower color, which might be purple or yellow. Now here's the interesting thing that a lot of people don't understand. So if he wants to look at 2 different traits, how many crosses does he have to do? And the answer is he only has to do 1 cross. I mean, if you take any plant, it has hundreds of different traits. If I want to look at people, for example, I can just look at one person and get data on 100 different traits: hair color, eye color, size, nose shape, and so forth. I don't have to keep doing more crosses for each trait that I want to look at. So all those genes, all those traits are already there, and they're all seen through one particular cross. We're going to look at dihybrid crosses, which would be the simplest situation. That is, we'll have 2 traits, and for each trait we'll have 2 alleles, so there'll only be 2 possibilities for each gene. Okay, now in this case, Mendel's second law really hits home, very important. The law of independent assortment. And what he says here is that if you look at what happens during meiosis, that is what gametes form, all possibilities for them to recombine can happen. So for example, if one is big A, little a, and one is big B, little b, you could have all possibilities. Little a with big B, big A with little b, big A with big B, and so on. All 4 possibilities can happen, and they can happen equally. And the other thing which is really important is that no gene affects another gene. And that's really important. So if you look how the alleles in gene A would segregate, it has nothing to do with how the alleles for gene B would segregate. And that's really important later on. So this has a lot to do with mathematics, and it has a lot to do with multiplying probabilities, and we'll get to that pretty soon. But before I do that, let's just try an example and see how this works. So let's go ahead and try a 2-gene system. Let's call it gene A and gene B. And let's suppose that we have somebody with a genotype of big A, little a, and big B, big B. We'll do it like that. And let's go ahead and cross them with, oh, how about little a, little a, little b, little b. Before I go ahead and do that, let's make sure we can describe these accurately. So how about this first guy? Now it's a dihybrid. We have a 2-gene system, right? But how would we describe that? We would say this is heterozygote for gene A, and it's homozygote dominant for gene B. And if we look at our second guy, we would say this is a pure homozygote. That is, it's homozygous recessive for little a, and homozygous recessive, little b. So it's a pure recessive homozygote. Very good. Now let's take it through meiosis, right? Remember meiosis? All gametes are equally possible. That's the second law. And all alleles will segregate. So this is really important for the first law here. What possibilities could we get from this guy? Now you can't get big A, little a. Remember, the first law says they must segregate. So you could get big A and you could get big B over here. Or you could get little a and big B over here, right? But you can't get big A, little a, and you can't get big B, because alleles must segregate. That's his first law. Now what are the possibilities here? Well, from the A's you could only get little a, and from the B's you could only get little b. Okay? So here's our cross. Now we do fertilization. So what would be the size of our Punnett square? It would be a 2, right, by 1 Punnett square. Okay? And if you put those together, and I'm not going to go ahead and draw the Punnett square because I think you all can see it at this point, but what would be our possibilities for these guys coming together? Well, the possibilities would be big A, and then we get a little a over here, and big B and little b, right? And on this one it would be what? Little a, right? And on this one you would get, sorry about the letters there, big B and little b. Oh, sorry about that. Don't know why that happened. Anyway, let's go ahead and look at the ratios here. So it's a 1-to-1 ratio. Who is this guy? This guy would show big A and big B. And this guy would show little a and big B. So you'd have a 1-to-1 relationship here of your prodigy. Fair enough? Okay. Let's move on here. Now in our next screen, let's see if I can bring that next screen up there. This is the pure Mendelian dihybrid cross. And what he did on this one was he took two dihybrids and crossed them to get a lot of different possibilities. So now who's this one up here? This guy is, right, the homozygous recessive, and this guy is the homozygous dominant. So this would almost be a test cross, right? Now look at, this is really interesting. This guy went ahead and he did all these squares. He said, well, I can get little and little from the R and Y and little, right? He's doing all for possibilities, right? But they're all the same, aren't they? So we really don't need to do that. I mean, you could include all 16 of them, but you can just divide by 4 and they'll get the same answer. And check out this one, right? Also the same here. So we really don't need to do these either, do we? It's just a repeat, yeah? So the answer is 100% of our guys turn out to be pure heterozygotes. But as far as phenotype, who do they look like? They look like big R and big Y for the phenotype. Because the other recessive alleles we would never see in that cross. Let's go to our last screen here. Now this is the real Mendelian cross. This is where he goes ahead and does the dihybrids that are both heterozygous. And in this case, you can't cross out anybody. This has got to be a 4x4 or 16 possibilities. So he goes ahead and takes them. You get 4 different gametes for this guy, and you get 4 different gametes. Remember, choose one R, choose one Y. Segregation of alleles, yeah? And then we do fertilization. They all come together to reform a diploid structure. Gamete, sperm, and gamete, egg come back together. Okay. Now here's the interesting thing. Who shows up for what phenotype? Now what are the phenotypes? They could show the dominant R and the dominant Y. Okay, who are they? Let's see, that's this one, well, all of these, right? All 4 of those. That's dominant, yeah. That's not, that is. Okay, whoops, sorry, don't know why it's doing that. That is, okay, who else does? There, yeah. That, how many we got there? We got 4, 5, 6, 7, 8, 9. We got 9, right? So you have 9 of them that show up for that type, right? How about the next one? Who would show up as being big R and little y? Who would? Well, there's one over here, right? Okay. And that one, right? Who else is big R, little y? That guy. Ah, we have 3. And let's do the next one. The next one would be who would show up as a phenotype that had little r and big Y, right? Who would that be? There's one, and there's one. Even though the genotypes are different, this is the phenotype. There are 3 of them. And who's the last one there? Well, as you can see, the last one would show up both as both recessives, right? Would be just this guy here, of which you have 1. So what's the ratio? 9 to 3 to 3 to 1. Or if we divide them over 16, we would say 9 over 16, 3 over 16, 3 over 1, 3 over 16, and 1 over 16. Those are the ratios we would expect to see if we did a pure heterozygous dihybrid cross. Now, the interesting thing is the only way this mathematics works is that you got to do a ton of pea plants, right, to see this. I mean, if you did just 16, chances are you might get not 9, 3, 3, 1. You might get something different. So you do hundreds and hundreds, which is what, of course, Mendel did when he did his experiments. And then it averages out to be the right thing here. And that is an explanation of a dihybrid cross.